So great. So we have our own Yuli Lyanda-Geller, who is a professor in particle physics department, giving today's PQC seminar. Yuli, I think, got his PhD from the famous Yoff Institute. I think he is a condensed matter theorist. I think he has done a lot of work in topics. I think even when you're a student, you did some really important, nice work in spin dynamic semiconductor. So your name is associated with spin ecoherence mechanism, so-called LYP mechanism. And later, he spent time in Urbana and Naval Research Lab, then joined the faculty. And he worked also on quantum Hall effect, topological physics, even AMO system, a broad range of topics. But today he will talk about some of his very interesting recent work, really unusual kind of electrodynamics in Dirac materials, which is interesting to many of us here. So take from here, Yuli. Thank you very much for doing this.
Okay, let me thank you very much for the invitation to speak. I'm delighted to talk at the seminar. I will use the opportunity to tell the work which was actually which I never talked before. So this is a new work on nonlinear quantum electrodynamics and Dirac materials. And this research stems from my approximately summer 2020, and then so not summer 2020, it's actually summer 2019 visit to Sydney. And we continued this work and finished it a couple of months ago. My co-authors are Alex Sushkov and Aiden Kaiser from University of New South Wales. Okay, so the themes are the following. I will briefly introduce you into Dirac materials, and then we'll discuss what kind of effects I will be talking about today, and I will compare effects of nonlinear quantum electrodynamics and effects in Dirac materials, compare the parameters, give you a brief idea of calculation, and then we'll proceed to the results. And intermittently, I will be discussing the experimental situation, so how to measure those effects and what are the numbers in various settings. This will be really a seminar talk. I will be talking primarily about this work, and won't spend much time on review. But I hope this will be interesting. Okay, so let's get started. Dirac materials. I intensively studied maybe over they were known maybe even in the 60s, and I will show you one reference to that. They could be both semimetals like bismuth or thallium arsenate, or they could be more traditional like lead telluride, and these are materials with Dirac spectrum. More recently they were studied for mainly transport properties. There is an idea that they can be very useful for photovoltaics, and there is abundance of topological phenomena in these systems because the spectrum is so interesting that it gives rise to many topological stories. Okay, so Dirac materials, of course, start with Dirac Hamiltonian. And I wrote it already in the form that is valid not in vacuum in quantum electrodynamics, but rather in a Dirac matter. So alpha and beta are 4x4 matrices characteristic for Dirac Hamiltonian. They are analogous to gamma I matrices, gamma 1, 2, 3, 4, 5. But the coefficients here with the exception of electrostatic potential, Phi and the vector potential A, so they are the same. But the coefficients are, in a typical Dirac material, the velocity is 400 times less than the speed of light. And so the gap is actually 2 delta. But the delta is roughly 100 millielectron volts as opposed to 10 to the 6 electron volts in quantum electrodynamics vacuum. It is actually this difference of parameters, and I will comment on it much more, so that allows to propose the effects I will be talking about today. Okay, rather than transport, I will, so in this work, we are concentrating on electric polarization, dielectric properties, and magnetization properties of Dirac materials. I will be, so the way to go is to compute the Lagrangian. So for free QED, free space QED vacuum, so Lagrangian is just E squared minus B squared divided by 8 pi. And in materials, the situation is changed because the dielectric constant and magnetic susceptibility. So this is material media Lagrangian. And electric polarization and magnetization of the sample are connected. So just either they are the derivative of the first derivative, so magnetic field and over electric field correspondingly. So, and what we will be doing, we will be looking at what kind of quantum corrections arise from Dirac-Hamiltonian if there are no free electrons, no electromagnetic excitations, and there is only an insulator vacuum, which I presented as green field. So it's, well, you know, in quantum electrodynamics, it's an insulator vacuum, but of course it's completely filled valence band in our Dirac materials. Okay, so now, of course, if you have a weak, in order to measure this, one can actually think about weak excitations, including into conduction band, but the results are primarily, the results I will be computing do not include any free electrons. That's important. And these are effects essentially in insulators. Okay, so let me show you. So I showed you two Lagrangians for free quantum electrodynamics and for for material system. And now let me show you what is the example of what I will be talking about. I will straight show you one result. This is the result of the summation of the whole series. Alpha D is the first, it is a fine structure constant which I call alpha Dirac instead of so the E squared over HC. It's instead of 1/37. We will briefly, we will shortly see what are these. So let me comment. The B is magnetic field and E is electric field. It's of course so infinity here. It's does not relate to high frequency like we say and epsilon infinity sub infinity. So it relates to the summation of the whole series of all the effects from Dirac vacuum. So I would also note. So this is valid all. Yes, please, Rudra.
Hi, Yuli. I wonder if you got the E dot B term, the axion electrodynamics term that is relevant for, let's say, topological insulators from the Dirac calculation.
Nowhere. So topological insulators. So you will have some states in the gap, right? So at the surface. So I'm interested in primarily in 3D systems. So there is a reason I am interested in 3D systems, especially for magnetization. You will see that the effects are rather, they are small and big simultaneously. They are small because, you know, and in order to use magnetometry, you need to use big samples. It's not 2D, it's primarily 3D. It should be mentioned up front. Of course, you can also have surfaces, but so again, so it is. So this is, for example, I will be mentioning that this is valid, for example, in lead telluride, which happens to be an ordinary insulator rather than topological insulator.
I see. Another quick question. Do you use a pure Dirac spectrum, or do you also take into account the fact that there's a band structure and the flow of states in the band?
I actually, I will start discussing this actually right now. I'm using Dirac equation, and it has long been appreciated, for example, for lead telluride. It is known already for 60 years that the lead telluride, for example, is very well described by the Dirac equation spectrum. Effects of anisotropy are taken throughout the paper explicitly. I would start mentioning this now.
So the effects of anomalies is not, so do you take into account anomalies in your calculation?
These are anomalies, the anomalies result from the summation of holes of the whole Dirac vacuum, but anomalies are not, and essentially, so this will originate everything from computation of the spectrum in electric and magnetic field. But the anomalies are, to some extent, they are hidden in the spectrum, but that's it.
Thank you.
Okay.
Yuli, hello, Yuli.
Yes, please.
So far, your theory considers or applies both to the gapless Dirac cone case, 3D, as well.
Yes, I will show you specific. Yes, I will show specific example when, for example, when it's quite natural that when my effects would be dependent, for example, on magnetic field, but would not be dependent on gap, they are equally valid for a gapless system. So that's kind of a story that could happen. So, and therefore, some of that, what I'm talking is valid for bismuth and for thallium arsenide. So it's thallium arsenide. So it's so they could be for valid for system with zero gap, or as I shall discuss, with very small gap. Okay, so this is the result of infinite summation of infinite, of not infinite. So of course, in terms of diagrams, it would be even infinite number of diagrams, but it's all summation of all vacuum states. This is valid in strong magnetic field. There is this result, particular result is valid in strong magnetic field, but weak electric fields. And I will discuss why weak electric field. So, and throughout the work, actually, so it will be weak. It could be both weak and strong magnetic fields, but it will be always weak electric fields because we want to avoid pair production. I'll talk about that later. Okay, this is the formula for isotropic Dirac Hamiltonian, but real materials are, of course, anisotropic. And then I can present this result for anisotropic materials in terms of dimensionless B magnetic and E electric field. And so they're essentially, so they are described by these formulas. Note that both E and B, so they depend on the fine structure constant to appear to this. We'll discuss that on the next view graph. And also this new, so the velocity, there is a 3x3 matrix velocity, which represents anisotropic materials. This also, all formulas throughout will be valid for in the case of anisotropy. Now, what are the features of this result? First, it is nonlinear in fine structure constant, simply because E and B depend on finer structure. It takes into account anisotropy of real materials. This is a non-perturbative solution, and it is summation of all, it happens to all orders. Okay, it is in the summation to all others is included. So I will comment later on what kind of, or what do I mean by all orders. So you will see that later. Okay, and this particular equation actually goes beyond the known quantum electrodynamics results. If you would open the textbook, we are not merely rewriting results from quantum electrodynamics into the language of Dirac materials. So this formula, for example, can nowhere be found except I'm presenting it to you now. Okay, so Yuka, please.
Hi, Yuli. So are these E star and B star assumed to be large here?
So E star, so they will appear on the next view graph, but E star and B star are famous Schwinger values of electric and magnetic field. And these are the values in which these nonlinear effects had to appear in quantum electrodynamics and should appear here. And you will see the comparison of these parameters just on the next view graph. So I made an introduction, introduced Lagrangian polarization and magnetization, and discussed what kind of effects I am looking at. And now I will discuss what are Dirac materials versus quantum electrodynamics in a little bit more details, and we'll compare parameters on the next few view graphs. Okay, so in quantum electrodynamics, actually, so these are very huge values. Effects require magnetic field 10 to the 9 Tesla and electric field 10 to the 16 volts per centimeter. That's quantum electrodynamics. That's where these effects, they roam in this range of parameters. So for free electrons. So nevertheless, two effects, scattering of phonons by the Coulomb field of nucleus and phonons splitting in two photons in the Coulomb field. So they were discovered in laboratory, among all nonlinear effects. But not the effects I'm talking today, of course. Normally one would expect these parameters to work in neutron stars and heavy ion colliders. Dirac materials, next slide will tell you that these are much, much weaker field. So let's start with the Compton Lens. So it's 10 to minus 12 meters in for free electron. So it is 25,000 times more for Dirac material that I described you with a gap 200 milli electron volt. And the ratio of velocity to speed of light 1/400th. This is a real change. So now fine structure constant. So that's the most famous parameter. Of course, we know it's 1/137th. For these parameters, it's 2.9. So for Dirac matter with velocity v. So then Bohr magneton takes the form of Dirac magneton, and it's completely different. It's the different value. And now the most critical story is the Schwinger fields at which it all happens. So for Dirac material I mentioned, it's almost, it's slightly less than 7 Tesla. As opposed to, I mentioned 10 to the 9 Tesla Schwinger value for free electron. And for electric field, so it is, we need to avoid pair production. And of course, 10 to the 5 volts per centimeter is of course, compared to 10 to the 16 volts per centimeter, is quite an advance. Okay, this is a comparison of parameters. Now let me present you the idea of calculation. It follows Schwinger to some extent. So we are looking at slowly changing fields null derivatives of the fields in the Lagrangian, and pretty much the same as in quantum free or material E squared minus B squared type Lagrangians. So we avoid pair creation. That means that E over E star, and that I wrote it explicitly, is much less than 1. And I will later show you the probability of the pair creation. So you will see that it comes from here. The energy density of electromagnetic field is known. And now we are looking for energy contribution from vacuum states, vacuum green states here. Okay, so vacuum energy is infinite, but we can compute it. So that's as a sum of all energies which are negative. And these are negative solutions of the Dirac equation. And in the presence of field, vacuum energy changes. And it is this change that causes the effects I'm talking about. Okay, so change of energy density in electric field. This is the result of energy density. So according to the Dirac Hamiltonian. So psi minus are the negative solutions for, well, in quantum electrodynamics, we would say positrons. Here, these are wave functions of valence band, or electrons occupying the valence band. Okay, now, so in order to make an accurate computation, the total charge of vacuum is, of course, 0. It's vacuum. So we need to subtract average potential energy of electrons in negative states, which can be computed so as an average of the potential E phi. And we can use Feynman-Hellmann theorem. So basically, that the differentiation of Hamiltonian over the parameter, in this case, electric field, to get this expression in terms of derivative of the total energy. And as a result, the change of density, energy density in vacuum, so with switching on both electric and magnetic field, is actually described by this difference. It is quite easy. I won't spend much time on it to see the change in Lagrangian density is actually it's the difference of this vacuum energy in the presence of the fields and in the absence of the fields. So you see it's an opposite sign. So essentially that's what is needed to. So we need to compute the sum of all energy of all states of all negative states of the Dirac equation. So, and what we do, we solve the Dirac equation in electric and magnetic field and sum over the energy. So I will show what is taken into account and what is not taken into account. So it will be more convenient for me to do it in a diagrammatic language, and I will do it on the next view graph. So, but this is the result. So this is essentially must be very accurately evaluated. There could be no pair creation, and it is valid as an asymptotic expansion, but formally this is the result. So it is valid at small a, and and it can be, so at small a, it can be written in terms of expansion in powers of a, and for arbitrary magnetic field B. Okay, so this is L. So now let me discuss various contributions. And I will do it in terms of diagrams. First of all, the theoretical jargon. So for this is the diagrams with legs and loops. Legs correspond to either. So here are legs. Here are 2. Here are 4. Here are 6. It's either each leg is either electric field or magnetic field. The wavy line is the Coulomb interaction. And the solid black line is the green function of electron. Okay, so now for one loop contribution is summed explicitly, and exactly, but in Dirac materials, actually, okay, so I will show it here. So what I can, when summing up, I can do the following. So I have two two indices, n and m, and n corresponds to if I take, there should be even number of fields present. And the power of n of these two fields, it's one kind of one power in the series. But I also can include the number of wavy lines, and that's m. But in Dirac materials, we're extremely lucky. The thing is, that every such, and in a solid state, we know that we actually make a random phase approximation, and we seek electron contributions due to Coulomb interactions into dielectric constant or into magnetic susceptibility. But here, every such contribution will be suppressed. The thing is that real Dirac materials have a very huge ionic contribution to dielectric constant, and it is almost 100 in relevant Dirac materials. But alpha D is 3. So at 2.9, okay, it can be a little bit more. So therefore, I don't need to account for electron-electron interactions because of this screening. And hence I include all expansion in the number of fields, but I don't need to include, this is the true parameter of the expansion, alpha is fine structure divided by ionic contribution to the dielectric constant. So I don't need to solve, to go through usual troubles. We are going in condensed matter to find the electronic contribution into dielectric constant. Okay, so now, I discussed the contributions and what I do take into account. So the first line with a single electron loop and no Coulomb interactions is solved exactly. That is what is solved exactly. Okay, so now the contributions. Yes, Yuka, please.
The fact that you can ignore electron-electron interactions, does it then basically mean that your results are valid at low frequencies?
Yes, of course. First of all, I always, I don't have free electrons. And of course, the frequency should be surely less than gap always. Otherwise, I have pair production at once, and it is all breaks down. So
okay,
yes.
I see. Mm-hmm.
Yes.
And the gap is relatively small frequency compared to like plasma frequency and
compared to the gap. Yes, that's always that's a small frequency and small electric field. Yes.
Okay.
But in principle, I was considering constant and more or less uniform fields. Okay, so this is the result of the principal diagram. Well, you know, the first, of course, we compute everything, but this is the contribution specifically from the first diagram. And actually, it produces renormalization if you compare it with a free electron contribution or with contribution in the materials that includes ionic dielectric constant. Then you actually get the following results. Yes, Rudra, please.
Yuli, I'm a little bit curious. So when you look at the electron Coulomb vertex on the previous slide, the vertex correction is supposed to go as the fine structure constant, right? So if you look at where your dashed line is joining to the two electron lines, that vertex, if you look at vertex corrections from, let's say, one of those wavy lines crossing the vertex, then that vertex correction, if I remember correctly, from just normal QED calculations, is of the order of the fine structure constant. Now, your fine structure constant that you wrote on the introductory slide was of the order of 2. So does that mean that the vertex correction is strong in this system? But that does not seem to gel with the suppression by factors of 100 that you've written here.
But look, so again, so I would say that the vertex, so even if you have a vertex, well, you know, so you're asking about where ionic contribution comes from, right?
Essentially. Yes.
Well, you know, this is, so I would, so this requires a contribution of ions, essentially. So, well, you know, they are affecting, but this is Coulomb interaction of, so of course, that means that Coulomb interaction of ions and electrons. So,
I see. So
that is supposed, yes, apparently this is strong, but, you know, in my picture, there are no ions.
Right, so you're using already the...
What is taken into account partially, you know, because valence band represents ions to some extent. Well, you know, but so I can tell you that nowhere in ionic contribution you can get the terms, for example, as magnetic field dependent as we get. So that's because the ionic contribution, for example, does not depend on magnetic field much.
I see. Thank you.
Okay. Okay. So this is this is the result of the. This is the result that is principle is divergent and needs renormalization, and the renormalization, you can see that this is the electronic part. It's of order of 3. When you put in ultraviolet cutoff and lattice spacing, so this log actually boils down to 3. And so this is, of course, that I remind you that there is total contribution, includes also ionic contribution. But the way we will be distinguishing this contribution from ionic contribution is magnetic field dependence. So this result is actually, partly it has been already experimentally observed as a giant magnetic susceptibility of bismuth. But I will talk about that later because there is an interesting story here. This contribution, importantly, it's diamagnetic. It has a negative sign. Okay, so this is from the first diagram. So now let me again mention how do I include anisotropy of materials. This is anisotropic Dirac Hamiltonian, which characterized by matrix of velocities here. So alpha I is the 4x4 matrix, which includes Pauli matrix sigma I in it. This is momentum. So velocity is really, it could be in any direction. And then we defined 3x3 real symmetric matrix XYZ. Denote crystallographical directions. And then we take a determinant of this matrix and denote it as V cube. So this dimensionless field that I mentioned also take into account this anisotropy. And here is the Hamiltonian that we obtain when we make this transformation. So you see, it obviously looks like the isotropic Hamiltonian, which is there is some slight difference of tilted and non-tilted values, but otherwise all calculation can be done for isotropic case and then easily generalized to anisotropy. Okay, this is remarkable anisotropy. So now a few results in terms of, so what are we getting? First of all, weak field limit. So this is the result that you can see in textbook, for example, in Landau, in Berestevsky, in Lifshitz-Pitaevsky, on Lifshitz-Pitaevsky quantum relativistic quantum mechanics. This is the result is there. Importantly, it depends on mutual orientation of magnetic and electric fields in addition to anisotropy. So in the absence of electric field, what is interesting is, of course, magnetization, but also magnetic susceptibility. And you can see that this is the result. Okay, so let me just show you. So the function f, which is here in black, shows you so what happens in the absence of electric field. And this is positive sign. And it's a paramagnetic contribution as opposed to diamagnetic contribution that I was discussing in the previous view graph. And this is in what happens, for example, in bismuth, where so theory was already done, and people actually calculated this very first contribution, high one, but actually it turns out the summation of all diagrams results in paramagnetic contribution. They're actually crucial for cancellation. So if one takes the real structure of bismuth with many so brilliant, with appropriate number of brilliant zone points, for this Dirac spectrum, actually almost wire spectrum. So then it turns out that when you take into account all these kind of Dirac points and you take into account paramagnetic contribution, you actually then will recover an experimental result. So, but paramagnetic contribution, this approach, which is by the way due to Heisenberg and Euler, 1936, and later it was modified by Schwinger in 1950. This actually approach, it actually allows to see both future and existing experiments in the new light. Okay, I discussed a few limiting cases. Now I would like to return to limitation on electric field. So the probability of a pair creation, it's easy to compute. So this is the probability, and you see that exponent requires if E is high, so then the probability grows dramatically, and so it needs to be included. It's here, so we must say that that this. Oops, I apologize. That this so that Dirac length. So this energy, Dirac length times charge times Schwinger electric field, must be compared to the gap delta between electrons and so between conduction and valence bands. And that results in this value that I already mentioned. So that, but it is, I would mention the following. It is interesting to note that real systems, as always, so there are surprises. So this is the in terms of ratio of electric field and Schwinger value. So imagine we look at the the tunnel diode and look at the reverse bias less than the current threshold in tunnel diode. So that means that no electrons are created. So the valence band is fully filled, and that actually was done. This story was, they were studying Rediker and Klaver 60 years ago. So they were studying tunneling current in the tunnel diode. And actually there is a very interesting dependence on the magnetic field in lead telluride in particular. It actually, the calculation is very similar. It shows that current is, tunnel current is dramatically different when you take electric field perpendicular or parallel, for example. But my main message here, that there was no current, so there was no pair creation up to 10 to the 5. So in real experimental situation, it could be kind of interesting to try. And this electric field is not external electric field of the capacitor. This electric field is built in. It is in the Saki diode itself. So it can be potentially used in these experiments as a source of huge electric field, which still does not lead to pair creation. Okay, so I talked about this. Now, in the presence of electric fields, here are the results. So it depends on relative orientation of electric and magnetic field, and when they are parallel. So these are the results for dielectric susceptibility. And I will comment on the magnitude on the next few graphs. When they're perpendicular, so this is the case of parallel, everything is described by this function G parallel. And this, so when they're parallel and everything discussed, so described in terms of G perpendicular, when electric and magnetic field are orthogonal. So these are the result. And of course, so this B, to mention, it includes the effect of crystal anisotropy as well, not only orientation of electric and magnetic field, but also it depends where they are directed. So there could be could be increase in the value or decrease in the value depending on orientation in the Dirac material. Okay, now what about magnitudes? What are we talking about? So yes, and one important thing to mention, I mentioned it already, ionic, so this is a correction to dielectric constant, and there is a huge ionic contribution there, but it is in no way it is logarithmic, for example. And that's the way to distinguish them. So now, what are the magnitudes of the effect? So actually there is a huge enhancement of the dielectric constant in magnetic field. And let me consider a specific example of bismuth 1 minus X antimony X. It's a Dirac semi-metal in principle, but at X content bigger than 700th, this is a topological insulator. Okay, so, and the gap is roughly 200 Kelvin. So at any temperature, so, and it can be done sufficiently less than that. We have an insulator. The value of Schwinger field, the limiting, to prevent pair creation is rather small. It's just 200 volts per centimeter. One can use a capacitor for this configuration. But what's the effect of change, how dielectric constant change with the magnetic field? At B equal 1 Tesla, it's enough to bring this dielectric constant to 12, and it continues to grow linearly with B. Well, you know, we don't have 100 Tesla in laboratory in constant field, but surely we have 33 in Tallahassee or in Gainesville. So this is actually a very strong effect.
45 Tesla.
Say it again?
The field you can get in Tallahassee, 45 Tesla.
Yeah, so yeah, oh, thank you. Thank you. It continues to grow with magnetic field. So both diamagnetic and paramagnetic effect depends on orientation of electric and magnetic field. So theoretically up to 100 Tesla, but you know, it's clear that it's hopefully it can be measured.
So just your calculation, this plot is performed for the case when the bismuth antimony is in the topological insulator region?
Probably. Okay, so now electric field dependent magnetization. So this is described again, it's two configurations, perpendicular and orthogonal electric and magnetic field. And this effect is described by function D here. So both in perpendicular case and parallel case, and again anisotropy. So the values depend on direction of these fields on crystallographic direction. So now what is the value of this effect? So Actually, the magnitude on the first glance, it seems very small. So I am taking the same bismuth antimonide. So on the first glance, it's 10 to minus 5 Gauss. Well, but if you, so the saturation of magnetization for D actually happens at 10 millitesla. And then, so the strength of the effect can actually be, should be compared to sensitivity of squid magnetometry. And it is very well can be observed by existing magnetometers easily. So these are used for this type of experiments. And I would also mention that there is a possibility of lock-in technique. So you take the frequency less than, don't create pairs. And you get a modulation at double frequency, and you detect this magnetization using lock-in technique and low frequency field.
Sorry, this is magnetization induced by what? By electric field or by?
So there is magnetic field, there is electric field. This is in no way related to low Wigner symmetry. So look, there are such effects due to low Wigner symmetry, due to absence of central symmetry or due to gyrotropy, etc. No, this is pure vacuum, and it is E squared and B squared essentially. So to say. But nevertheless, this is due to Dirac. What happens due to Dirac vacuum in Dirac materials? And I'm almost done. So what we suggest is to observe large nonlinear magnetoelectric effects in Dirac materials. So in particular, there is a large magnetic field tunable susceptibility enhancement of the dielectric susceptibility enhancement in insulator. There is electrically induced magnetization. And I would mention theoretical feature that this is a non-perturbative calculation. So, and it was kind of very interesting. Thank you very much for your attention.
Hey, thank you very much, Yuli. Great. We do have some time for more questions. Maybe I can continue on the one I just asked. I think it seems to really observe these effects. The best system should be the one with a small gap, like lead telluride, because then you can talk about truly an insulator.
Yes,
it's not,
right. And it is interesting on its own because essentially insulators can be magnetized. So this is
So in fact, unless I probably misheard what you said, I think to observe this, it's actually not good to use a, say, topological insulator, because in that case, it's hard to apply electric field because you have surface space screening the electric field.
So I actually agree, but these were such drastic values that I showed that. In fact, in the paper, we discussed how to observe these effects in lead telluride and made relevant estimates for that. So this is currently under review in physical review letters. And also it is somewhere in January. I forgot to put on the reference. It's on archive. So the paper is on archive. You can see it. So and we discuss a lot of experimental system. In fact, maybe up to a third of the paper is discussion of experimental systems in which it could be measured. I today concentrated on more explaining the idea of the story, and how parameters are related. So, but. And just show a few brief examples of experimentally relevant issues. So,
but also earlier I asked, I guess for some people, Dirac material, people think about these massless Dirac material like Dirac semi-metal or biosemi-metal. Of course, you focus on the massive Dirac electron material, but if you really are gapless, like in Dirac semi-metal, then delta, your gap goes to 0. Then these shrinker field E star and B star become 0.
So once they are gapless, you know, it's not kind of a pure effect, because it's very difficult then to separate electronic contributions from, you know, these vacuum contributions.
Yeah, so again, I think
we want it to be an insulator, you know.
Yes,
just,
okay.
And it is, once again, you know, I don't know how it sounds to you, but magnetization of an insulator, it's fascinating.
So I'm just make sure we're focusing on actually adapt Dirac material insulator. That's the best system for this.
Yuli, this is Vlad. First of all, congratulations on this work, which looks really spectacular, quite fundamental development as far as I could judge. But I'd like to further take on the question that Yulon asked. I mean, if you really would like to impress broader community with this theory and do some experimental demonstration, which particular experiment you would pick up to do as most striking demonstration what the theory predicts? So like, let's say if you walk to experimentalists, what you suggest him or her to do to become famous and demonstrates one particularly exciting aspect of this theory?
So we kind of we think about that, you know, that so that magnetic tuning of dielectric constant is one thing, because it can dramatically grow.
By the way, that's really impressive. If you really could go from something like 3 to 12 by simply applying magnetic field,
Yes.
that sounds very impressive.
So we hope that, you know, there is this ionic contribution, which is 100, and this happens on that background, but there is no magnetic field dependence. Therefore, kind of, that's the way to separate them. And secondly, of course, electric field induced magnetization. So it's also kind of
yes, indeed,
quite striking. And you know, so I am used to these effects. When you have a Rashba term, you apply electric field and you get magnetization from free electron spin. But here we don't have no Rashba term, no and more importantly, no electrons. This is vacuum. This is field. Well, there are valence band. Valence band, of course, is filled with electrons, but we are used to the story that, you know, that field valence band means nothing. So here it is. It means something. No, so, and it leads to this interesting story.
Yeah, and that would be very interesting in the context of topological insulators, as Jon properly pointed out, because to distinguish from the Rashba effect, it's a challenge sometimes. And here, yeah, you could have really clear demonstration of this electrical field induced magnetization. Very interesting indeed.
Thank you.
So if I got it right, you're talking about the effect of slowly.
Just a second, I will. So, yes.
So if I correctly understood, you're talking about the effect of slowly changing fields. Let's imagine that we don't think about it and start looking at the effect of frequency dependent, time dependent fields. Presumably, so what's going to happen?
So if you have a frequency much less than the gap,
then nothing.
Then you can modulate. You know, electric field, but there is no. If there is no pair production, so this is very useful for lock-in, as I mentioned, for lock-in experiment.
What if the frequency is comparable to the band gap?
Oh, then you have electrons and you have electronic contributions. Well, you might have something like that I was discussing, but you will never tell that it is due to valence band. It will be due to free electrons, and, you know, and these effects. This then becomes a standard semiconductor situation. That, for example, you enhance a lot of you excite, a lot of electrons in conduction band, and then these electrons create you the new media, and they are interacting with all nonlinear optics. So you can generate additional magnetization, actually not necessarily by magnetic field, but by light. That means by electric and sometimes magnetic field of light. So then this is simply a different system. So yep. we keep it to vacuum only. So and then there is a slight modulation by electric field. That's what we are thinking about.
Well, again, that's kind of boring. So the time is the time-dependent part, which usually gives more kind of rich phenomena. So let's wouldn't the frequency dependence of this vacuum contribution and everything else be different?
First of all, there so any interband contribution, well, you know, from so it will have you know, it will obviously have some I would say probably singularity. So at the frequency equal to 2 delta, h omega, h bar times frequency equal to delta, 2 delta. So nothing like that happens for modulation in of the vacuum. So well, sounds nice, modulation of the vacuum.
It doesn't. Thanks.
Thank you, Jim.
Hey, Yuli, this magnified induced modulation of dielectric constant. This dielectric constant is a DC dielectric constant, right?
Yeah, but it could be small frequencies is okay.
Yeah, sure.
Yes, of course. This is what we call normally E0, not E infinity.
Right,
it is
it's
E0.
zero. Mm-hmm.
Yes,
yeah.
E0.
I think this is a really interesting effect in box system, which I'm not aware any examples. I think it is extremely interesting. The other effect are the electric field induced magnetization. I just want to point out, at least that has been seen. For example, you can have these magnetic insulator thin films. For example, some of these two-dimensional magnets, for example, chromium, germanium, telluride, and other these recently studied 2D magnets. People do see when you apply electric field, you can modulate or even create a magnetization.
No,
presumably a different mechanism.
Yes, it would be. So normally, so well, you know, Leonid, for example, observed this in gallium arsenide with manganese. So that normally it is. You require some spin-orbit interaction to do that. So here. And that spin-orbit interaction which breaks the symmetry, it's either the so-called Dresselhaus or Rashba or whatever, or strain-induced Rashba or whatever it is. But here you don't, and then it is odd in electric field magnetization. So here all effects are even power. So they are not related to spatial symmetry breaking, I would say, or crystalline symmetry breaking. So anisotropy is taken into account, but it's...
Okay, so when you say it's even power, you mean when you reverse the direction of the electric field, the magnetization does not reverse?
The magnetization is not reversed, no.
Okay, so the magnetization is determined by, so then what sets the direction of that magnetization then?
So the direction of magnetization, so it depends on, okay. So it is, this is magnetization, it depends on crystallography, of course, but to some extent, so it's, you can, so it is, okay, so what's the direction of magnetization? It should be along, of course, it should be, especially in perpendicular case, it is non-trivial to say that it is a long electric field. It's not a long electric field. So it is a non-linear effect. The direction will be defined, of course, to some extent by electric field and relevant crystal anisotropy. But it won't change sign with it, because you can. So let me see. Actually, maybe just to be sure. It should know. It doesn't. So it is not E times H effect. So E times H effect, that one requires absence of center of symmetry, and here there is no center of symmetry. As usual, magnetization is created by circulating currents. So in real sample, that would be, of course, more or less coming from surface effects.
Yeah, but it still needs to choose a direction one way or the other, right? Even if it chooses if you fix the axis, it should.
Well, in isotropic, so we can so it is easy to analyze what the direction to choose. But for example, this effect exists even in isotropic system, so you can change anything and measure susceptibility, magnetic susceptibility.
Yeah, but when you measure susceptibility, sort of you're presumably aligning that to the external magnetic field. You're applying small magnetic field, right? So susceptibility, I can understand. You apply small field and you look at the magnetic response of the media, right? So that gives you a well-defined directionality.
Yeah, but we already, yes, so we already apply electric and magnetic field. So it's essentially when you apply, okay. So
magnetic field will define the axis of magnetization.
Magnetic electric field will define the axis of dielectric permeability, and magnetic field will define the axis of magnetization. Yes.
Okay, and then basically electric field will modulate that magnitude of magnetization.
The magnitude of magnetization, yes.
But it will not depend on
it will not reverse it will not change from diamagnetic to paramagnetic depending on sign.
Okay. Mm-hmm.
So I showed you the diagrams with legs. So the number of legs is even. You know, that's so to choose the direction. You know, so you can try to. It depending on masses, of course, one can choose the preferential direction for both of them. Because in one case it's 1 over the determinant, and in another case it's proportional to determinant. So it's kind of. There could be interesting play here. Just maybe to comment more. If there is no magnetic field, then there is no electrically induced magnetization. So here it's simply an electric field due to vacuum renormalizes susceptibility. And so the value of magnetization changes dramatically. But if there is no magnetic field, electric field would not lead to magnetization. So that's that's for sure.
I understand. The effect is it requires presence of both electric and magnetic field.
Yes.
And you said it's even in both electric and magnetic field.
Yes. Yes.
One more question, if so would you say, so if I compare, if I think a real vacuum, right, it's half meg EV band gap, if you want, with a for example, so it seemed to be main effect why you have this very small shrinker field is not so much about reduction of the band gap, because even in conventional semiconductor, it's already reduced by a millionfold, right, from mega EV to EV. It's mostly driven by the small effective speed of light. Is that the main driving effect?
Yeah, so it's both the gap and speed of speed of light. So the fact that the gap is 100 millielectron volts instead of 1 mega electron volt, it is
100 millivolts is just 1/10 of the gap of gallium arsenide.
So yeah, it's half a gap. It's characteristic gap in lead telluride, for example. So I mentioned this so bismuth antimonide. So that one, so it has 200 Kelvin gap. It's even less. This is something like 15 millielectron volts. So compared to 1 mega electron volt, that's one thing. And well, you know, so it is maybe, so you can say different ways differently. So there are two parameters, effective mass and velocity. So, and the gap is derived through both of them. That means that both velocity is smaller and effective mass is considerably smaller, and that affects the gap in a relevant way.
May I follow this question? This is Maxim Ludikov speaking.
Yes, yes, of course.
So in quantum electrodynamics, the Schwinger electric field is in some sense the least efficient way to create pairs. Usually pairs are created by just collision of two MEV photons. And nowhere, of course, electric field during that process is close to Schwinger field because it's a resonant process, so it's way more effective. And then by analogy, I would expect that collision of two phonons, time-dependent phonons, will create a whole electron pair much easier than a static electric field. Is that true?
So collision of phonons.
Just like in quantum electron dynamics, pairs
I see what you're saying. Yeah.
By Schwinger field, but they're easily created by collision of two photons. As I mentioned, the collision cross-section is almost Thomson.
You know, if you think about photons, then the question arises: what kind of so are these photons below the gap energy, or if phonons? That's the latest story. I'm not sure. We haven't considered that. Phonons were not on our horizon. No.
Phonons will be primarily suppressed at low temperatures, right?
It will, yes, of course.
Yeah, of course, it's a threshold process. It's a threshold process, but it is way more efficient, and it is
for pair production. But we want, but Maxim, we want to avoid pair production. We don't want electrons. We want insulator.
Right, and then my intuition says that if you have sufficient high frequency phonons, then they will dominate the pair product, the whole electron production.
I think it's an interesting question. Of course, you can.
You can always
excite phonons even at low temperature, right? By doing something, and then you're saying they would lead to, if they lead to strong pair production.
For example,
that's the
you don't need to heat material to MEV temperatures. You can create just few hard photons, and they will start pair producing. They need not to be in equilibrium.
Yeah, but so you would like to have pair producing. I actually would like to avoid that at any cost, because I would like to have all this magnetization of insulators.
Yeah, I understand, but this could be a dangerous process, which, yeah, for you. So
collision of phonons is not that, So at least for all transport effects that one considers, collision of phonons is not a factor. And for most of optics in condensed matter, collision of phonons is collision of two phonons. Electrophonon collisions, they are enormously important. But collision of photons is not.
Yeah. Here I'm getting a little bit beyond my knowledge of solid state.
And electron phonon collisions here would not work either, simply because there is no empty spots in the valence band. There could be no transition.
Yeah, but
quantum electrodynamics, the photon-photon collisions are so efficient because they're resonant.
Probably.
Resonance between the two photons and the masses. And resonant processes can be surprisingly efficient.
But two phonons, okay, if the gap is too small, they could be.
Yeah, so if the gap is kind of resonance, two phonons would, I would suspect they would make pairs much more efficiently than the constant electric field.
Well, but basically I would say that if we want still to avoid that, I simply lower the temperature and phonons are frozen out.
But I think Maxime is maybe trying to predict a different kind of effect, which is interesting. Of course, that's something you want to avoid, Yuli. But if that is the case, what he predicts, there may be strong effect in the thermal conductivity because the thermal transport is strongly influenced by phonon-phonon scattering. So if this kind of pair production cause strong modification of phonon scattering process, then there should be some anomaly in the thermal conductivity.
Yeah, it's not necessarily thermal conductivity, but also the effect which Yuli is talking about may have strong temperature dependence.
Well, but he wants to avoid phonons, so he will go to very low temperatures.
Yes. But basically, heating up, it would be very strongly affected by what Maxime is talking about. So that may sort of have a very strong temperature suppression of these effects.
I don't know. Can there be non-thermal phonons produced efficiently?
You can always put acoustic wave there.
Yeah, so that would be it. So then we have a prediction that acoustic wave will excite whole...
Well, acoustic wave is because it potentially interacts with electrons and valence electrons as well. So it's as soon as you have non-zero temperature, there is some place there. So potentially, so it could be,
but probably with your simple scaling that you showed in the beginning, how you change from quantum electrodynamics to solid state, it's easy to predict to estimate what would be the cross
yes,
section.
that's sure. That's for sure. Yes.
Okay.
We had a very good discussion. I think we actually is already more than 10 minutes over. Thank you very much. Actually, if people want to stay to this more, they're welcome. But I just want to say thank you very much, Yuli, for very.
Thank you again. Thank you. Thank you for your attention. Thank you.